Your home is disintegrating. Not your house, not your city. Your cosmic home, the Milky Way galaxy, is coming apart at its edges. Stars are being stripped away. Entire clusters are escaping into intergalactic space. The gravitational bonds holding our galaxy together are failing in ways astronomers never predicted. And this isn't happening slowly over trillions of years. It's happening now, fast enough that we can measure it, track it, watch our galaxy hemorrhage stars into the void. Thousands of stars are fleeing the Milky Way every year, and the rate is accelerating. Scientists discovered this recently by accident. They were mapping stellar motions, routine work, when the data showed something impossible. Streams of stars flowing outward from the galactic disk, moving too fast to be gravitationally bound. Escaping into intergalactic darkness. These weren't stray stars wandering off. These were organised outflows. Rivers of stars draining from our galaxy like blood from a wound. The discovery triggered alarm across the astronomical community. Galaxies aren't supposed to fall apart while they're still actively forming stars, still full of gas and dust, still in what should be their prime. Yet here's the Milky Way, apparently in the process of slow-motion disintegration. If you're ready to learn that your cosmic address might not exist much longer in its current form, subscribe and prepare yourself. What you're about to discover changes how we understand galactic evolution and our own place in the cosmos. We begin. The Milky Way is not a static structure. It's a dynamic churning system where stars orbit the galactic center in complex patterns, where gas clouds collide and form new stars, where gravity constantly reshapes the distribution of matter. Change is normal, but what astronomers are observing now goes beyond normal change. They're seeing systematic loss of material. Stars that should be gravitationally bound to the galaxy are instead on escape trajectories. Globular clusters that orbited the Milky Way for billions of years are being torn apart. Their stars scattered into intergalactic space. The outer edges of our galaxy are fraying like a rope coming unwound. The evidence comes from multiple sources. The Gaia Space Telescope, launched by the European Space Agency, has measured precise positions and velocities for over 1 billion stars. This unprecedented dataset revealed stellar streams, elongated groups of stars moving together through space that weren't known before. Many of these streams are tidal debris, the remnants of smaller galaxies or star clusters that the Milky Way consumed. This is normal. Galaxies grow by eating smaller neighbours, leaving streams of stars as evidence of past meals. But some streams are different. They're moving outward, not inward. They're escaping rather than being consumed. And they're not coming from external galaxies that we're pulling apart. They're coming from the Milky Way itself, stars that were once gravitationally bound, now breaking free. This shouldn't happen. The Milky Way's gravity should hold its stars. The galaxy's total mass is enormous, dominated by dark matter that extends far beyond the visible disk. Stars in the outer regions might orbit slowly, but they shouldn't escape entirely. Yet they are escaping. Thousands of them. And not just individual stars, but entire star clusters, collections of hundreds or thousands of stars moving together, all on trajectories that will carry them out of the galaxy into intergalactic space. The phenomenon was first noticed in the outer halo of the galaxy, the diffuse region of old stars surrounding the main disk. Astronomers found streams of stars at the very edge of the Milky Way's gravitational influence, moving at velocities that exceed escape velocity. Initially, they assumed these were stars from external dwarf galaxies being tidally stripped as they passed through the Milky Way's halo. But detailed chemical analysis revealed something disturbing. The stars had the chemical signatures of Milky Way stars, not external intruders. These were our stars, born in our galaxy, part of our system for billions of years, now leaving. Further investigation revealed the extent of the problem. It's not just the outer halo. Stars are being lost from the galactic disk as well, particularly from the outer spiral arms where the Milky Way's gravitational grip is weakest. Astronomers calculated the mass loss rate. The numbers are staggering. The Milky Way is losing the equivalent of several solar masses per year to escaping stars. That might not sound like much in a galaxy containing hundreds of billions of stars, but integrated over time, it represents significant mass loss. Over 1 billion years, at current rates, the Milky Way will lose millions of solar masses. Over 10 billion years, the loss could reshape the outer regions of the galaxy completely. The spiral arms might fade. The disk might shrink. The entire structure could change dramatically. This raises immediate questions. Why is this happening? What force is pulling stars away from the galaxy? Why didn't we predict this? The answers are complex and disturbing. They involve interactions we didn't fully understand, gravitational dynamics we modelled incorrectly, and external influences we didn't account for properly. Part of the answer involves satellite galaxies. The Milky Way isn't alone. It's part of a local group containing several dozen smaller galaxies, including the Large and Small Magellanic Clouds, the most prominent satellites visible from Earth's southern hemisphere. These satellites orbit the Milky Way, but their orbits aren't stable. They raise tides in the Milky Way's stellar disk and dark matter halo, gravitational perturbations that can fling stars outward. Think of the Moon raising tides on Earth's oceans, but scaled up to galactic proportions with solid stars instead of liquid water. These tidal interactions were known but underestimated. Astronomers thought they caused some disruption, but nothing major. The new data reveals they're far more effective at removing stars than models predicted. The Magellanic Clouds are particularly problematic. They're massive enough and close enough to significantly perturb the outer Milky Way. As they orbit, they create a wake of disturbed stars, some of which gain enough energy to escape the galaxy entirely. Recent simulations show that the Magellanic Clouds might be responsible for a large fraction of the stellar escape. Their gravitational influence doesn't just strip stars from the satellites themselves, it destabilizes stars in the Milky Way's outer regions, sending them on escape trajectories. But satellite interactions aren't the whole story. Something else is happening. Something more fundamental about how the Milky Way's gravity works at large distances. The dark matter halo that dominates the galaxy's mass might not be as smooth and uniform as models assumed. If it's lumpy with concentrations of dark matter creating local gravitational anomalies, these lumps could perturb stellar orbits unpredictably. Stars that should be safely bound might pass through a dark matter concentration and receive a gravitational kick that accelerates them beyond escape velocity. This would be rare for any individual star, but over billions of years and billions of stars could produce significant mass loss. There's also the possibility that the Milky Way itself is not in equilibrium. Galaxies are supposed to reach stable configurations where star formation, gas accretion, and stellar motions balance. But maybe the Milky Way never fully settled. Maybe it's still adjusting from past collisions and mergers, still finding equilibrium. And mass loss is part of that adjustment. This would mean the disintegration is temporary, a phase the galaxy is passing through rather than a permanent condition. Eventually, the Milky Way might stabilize and stop losing stars at current rates. Or maybe not. Maybe what we're observing is the beginning of a long-term trend that will accelerate as the galaxy ages. Maybe all spiral galaxies eventually lose their outer regions this way, slowly dissolving from the edges inward until only the dense core remains. We don't know yet. The observations are too recent. The models are still being refined, but what's clear is that the Milky Way is not the stable, eternal structure we thought it was. It's a dynamic system in flux, losing material to intergalactic space, changing shape and size on timescales that, while vast by human standards, are rapid by cosmic standards. Our galaxy is falling apart, not catastrophically, not overnight, but measurably, observably, undeniably coming apart at its edges. And we're only beginning to understand why. When astronomers calculated how much mass the Milky Way should contain based on stellar motions, they got a number. When they added up all the visible matter, stars, gas, dust, planets, they got a much smaller number. The difference is dark matter, the invisible substance that makes up most of the galaxy's mass. But now there's a new problem. When they account for escaping stars and calculate how much mass the galaxy has lost over its lifetime, the numbers don't add up. The Milky Way should be significantly more massive than it appears. Mass is missing not because we can't see it, but because it's gone, expelled from the galaxy entirely. This wasn't predicted. Galactic formation models showed galaxies growing over time, accreting gas from the intergalactic medium, occasionally merging with smaller galaxies. Mass goes in, not out. The Milky Way should be gaining mass, getting heavier as it ages. Instead, it's hemorrhaging mass, and the loss isn't trivial. Preliminary calculations suggest the Milky Way might have lost 10% or more of its total stellar mass since formation. That's tens of billions of solar masses worth of stars that are no longer gravitationally bound to the galaxy. This missing mass changes everything about how we understand galactic evolution. If galaxies routinely lose this much material, then current mass estimates are wrong. The Milky Way is lighter than we thought. Its gravitational influence is weaker. Its future evolution will follow different paths than models predict. The missing mass also affects dark matter estimates. We calculate dark matter content by measuring how fast stars orbit and comparing that to how much visible matter exists. If we've been underestimating mass loss, we've been overestimating dark matter. This doesn't mean dark matter doesn't exist, but it might mean there's less of it than we thought, or that it's distributed differently than models predict. The dark matter halo might be smaller, less dense, or shaped differently than assumed. Researchers are scrambling to revise models. They're rerunning simulations with mass loss included, seeing how it changes predictions about galactic structure and evolution. The results are surprising and sometimes contradictory. Some simulations show that mass loss stabilizes galaxies, removing stars from unstable orbits and leaving behind a more tightly bound core. In these models, the Milky Way's current disintegration is actually beneficial long-term, pruning away loosely bound material and creating a more robust structure. Other simulations show mass loss as destructive, weakening the galaxy's gravitational potential and making it more vulnerable to disruption from passing galaxies or tidal forces. In these models, the mass loss we're observing is the beginning of a decline that could eventually strip the Milky Way down to a much smaller remnant. The truth probably lies between these extremes. Mass loss is neither purely good nor purely bad, just a process that reshapes the galaxy over time. But understanding which extreme we're closer to matters for predicting the Milky Way's future. The missing mass mystery extends beyond just stars. Gas is escaping too, blown out of the galaxy by supernovae and stellar winds. This gas loss might be even more significant than stellar loss, because gas is the raw material for future star formation. If the Milky Way is losing gas faster than it can accrete new gas from the intergalactic medium, star formation will eventually cease. The galaxy will slowly fade as existing stars age and die without new stars replacing them. Given enough time, the Milky Way could become a graveyard, a collection of stellar remnants orbiting a central black hole with no active star formation. Current observations suggest this isn't imminent. The Milky Way still forms several solar masses worth of new stars each year. Gas continues flowing into the disk from the halo. Star formation should continue for billions of years, but the balance is precarious. If gas loss increases or inflow decreases, star formation could decline rapidly on cosmic timescales. A galaxy that looks vibrant today could be moribund in a few billion years. This raises questions about other galaxies. If the Milky Way is losing mass, are other galaxies experiencing similar losses? Is this a universal phenomenon that affects all spiral galaxies, or is something unique happening to our galaxy? Observations of nearby galaxies provide partial answers. Many spiral galaxies show evidence of mass loss, though the rates vary significantly. Some appear stable with little material escaping. Others show dramatic outflows exceeding the Milky Way's losses. The variation correlates with several factors. More massive galaxies tend to retain material better. Their stronger gravity preventing escape. Galaxies with recent mergers show higher mass loss, their disrupted structures failing to hold stars and gas. Galaxies in dense environments with many neighbours lose more mass to tidal stripping. The Milky Way falls somewhere in the middle of this spectrum. Not the most stable galaxy, not the most disrupted. A fairly typical spiral galaxy experiencing fairly typical mass loss. This is both comforting and alarming. Comforting because it means we're not uniquely doomed. Alarming because it means mass loss is a common feature of galactic evolution that we've been systematically underestimating. If every spiral galaxy is losing mass at rates comparable to the Milky Way, then our understanding of how galaxies evolve is fundamentally incomplete. We've been modelling growth while ignoring decay, treating galaxies as systems that accumulate matter while overlooking the processes that expel it. The missing mass problem also connects to the so-called missing baryon problem in cosmology. The universe should contain a certain amount of ordinary matter based on observations of the cosmic microwave background and predictions from Big Bang nucleosynthesis. When cosmologists add up all the baryons they can find, in stars, gas, planets, everything, they come up short. About half the expected baryons are missing, unaccounted for in current observations. Some of these missing baryons might be in intergalactic space, expelled from galaxies through the mass loss processes we're now detecting. If galaxies routinely shed material that ends up in the vast voids between galaxies, that could account for a significant fraction of the missing baryons. This would solve one cosmological mystery while deepening our understanding of galactic evolution. The baryons aren't missing, they're just spread so thin in intergalactic space that they're difficult to detect. And they got there by being expelled from galaxies like the Milky Way. Testing this hypothesis requires observing the intergalactic medium, the diffuse gas between galaxies. This is technically challenging because the gas is extremely thin and doesn't emit much light. But recent observations using quasar spectra have detected some of this material, and preliminary estimates suggest there's enough to account for at least some of the missing baryons. The missing mass mystery represents a fundamental gap in our understanding of galaxies. We thought we knew how galaxies work, how they form and evolve, what processes govern their life cycles. But we missed a crucial piece. Galaxies don't just grow, they also shrink, losing mass throughout their lifetimes. This isn't just an academic concern. The mass loss affects the Milky Way's future trajectory. How long will our galaxy survive in its current form? How will it change over the next billion years? What will it look like when the sun dies? These questions now have different answers than they did before we understood mass loss. The Milky Way's future is less certain, more dynamic, more prone to dramatic changes than we previously assumed, and the mass that's already gone, the stars and gas that have escaped into intergalactic space, represent a diaspora of material that originated in our galaxy but will never return. These escaped stars will wander between galaxies, isolated and alone, far from their birthplace, drifting through the cosmic void. Some of these stars might have planets. Some of those planets might harbour life. There could be civilizations out there living on worlds orbiting stars that escape the Milky Way, looking up at a night sky that contains one nearby galaxy, the Milky Way, but otherwise is empty of neighbours. Those civilizations would have a very different view of the universe than we do. They'd be cosmic orphans, exiles from the galaxy that birthed their star, adrift in the emptiness between galaxies. And they'd have no way of knowing their true origin, no way to trace their star's history back to its birthplace in the Milky Way. The missing mass represents lost history, lost potential, lost connections, material that should be part of our galaxy, but isn't, scattered across intergalactic space, beyond our reach or influence. The Milky Way is being murdered, not by some external cosmic catastrophe, but by its own children. The satellite galaxies orbiting our galaxy, smaller systems that should be harmless companions, are actually slowly tearing the Milky Way apart. This wasn't supposed to happen. In the standard picture of galactic dynamics, satellite galaxies orbit peacefully, occasionally getting consumed by the central galaxy, but otherwise coexisting without major disruption. They're like moons around a planet, small bodies in stable orbits, gravitationally bound but not particularly threatening. But the new observations reveal something darker. The satellites aren't passive. They're actively destabilizing the Milky Way structure. Their gravitational pull stripping away stars and gas, their orbital motions creating resonances that eject material. Their very presence undermining the galaxy that hosts them. The most destructive satellites are the Magellanic Clouds. These two irregular galaxies, visible to the naked eye from Earth's southern hemisphere, are the Milky Way's largest satellites. They orbit together as a binary pair, both systems gravitationally bound to each other and to the Milky Way. For decades, astronomers thought the Magellanic Clouds were relatively benign. Yes, they were being tidally stripped, losing stars and gas to the Milky Way. But this was seen as the Milky Way consuming its satellites, not the satellites damaging the Milky Way. Recent simulations reveal the opposite. The Magellanic Clouds are destroying more than they're being destroyed. Their combined mass and orbital energy are so significant that they create huge perturbations in the Milky Way's outer disk and halo. As the Magellanic Clouds orbit, They create a gravitational wake, similar to how a boat creates a wake in water. This wake disturbs stars in the Milky Way, accelerating some to escape velocity, sending them on trajectories that carry them out of the galaxy. The effect is strongest in the direction of the Magellanic Cloud's orbit. Stars in that region experience maximum perturbation and are most likely to be ejected. Observations confirm this. The streams of escaping stars are concentrated in specific directions that correlate with the Magellanic Cloud's orbital path. But it's not just stars being lost. The Magellanic Clouds are stripping gas from the Milky Way as well. The so-called Magellanic Stream, a ribbon of neutral hydrogen gas trailing the Magellanic Clouds across the sky, contains material from both the satellites and the Milky Way itself. For years, astronomers thought the Magellanic Stream was purely satellite material, being stripped away as the clouds orbit. But recent analysis shows Milky Way gas mixed into the stream. The satellites aren't just losing their own gas, they're pulling gas out of the Milky Way's halo and disk. This gas loss has consequences for future star formation. The gas being stripped away would have eventually fallen into the disk and formed new stars. Now it's gone, removed from the galaxy, drifting into intergalactic space. The Milky Way's future star formation rate will be lower than it would have been without the Magellanic Clouds. The Large Magellanic Cloud alone might remove billions of solar masses of gas from the Milky Way over its lifetime. Combined with the Small Magellanic Cloud, the total loss could be staggering, enough to significantly affect the galaxy's evolution. And the situation is getting worse. The Magellanic Clouds are falling into the Milky Way. Their orbits are decaying due to dynamical friction. The gravitational drag created by dark matter in the Milky Way's halo. Each orbit brings them closer, increases their destructive potential, accelerates the mass loss they cause. Eventually, probably within a few billion years, the Large Magellanic Cloud will merge with the Milky Way. This merger will be catastrophic in some ways, beneficial in others. The Milky Way will gain the LMC's mass, potentially growing larger, but the merger process will trigger violent disturbances, ejecting additional stars and gas, reshaping the galaxy dramatically. Simulations of the future merger show a chaotic event. Stars from both galaxies will be scattered. Gas clouds will collide, triggering intense bursts of star formation. The supermassive black hole at the LMC's centre will sink toward the Milky Way's centre, eventually merging with our central black hole in a spectacular gravitational wave emission event. The merged galaxy will be different from the current Milky Way. Larger, more massive, but also more disordered. The spiral structure might be disrupted. Star formation patterns will change. The entire galactic ecosystem will be reset. But before that merger occurs, the LMC's orbital decay will continue, wreaking havoc. Each close pass will eject more material, destabilize more orbits, send more stars fleeing into intergalactic space. The mass loss we're currently observing might accelerate as the LMC approaches. The Magellanic Clouds aren't the only threatening satellites. The Milky Way has dozens of known satellite galaxies, and most are too small to cause significant damage individually. But collectively, they might have cumulative effects. Each satellite creates small perturbations. Each disturbs a few stars. Each removes a bit of gas. Add them all up over billions of years, and the total impact could be substantial, perhaps comparable to the Magellanic Cloud's influence. There might also be unknown satellites lurking in the Milky Way's halo. Not every satellite is visible. Some might be mostly dark matter with few stars, effectively invisible to current telescopes. These dark satellites could be perturbing stellar orbits without us realizing it. Recent observations hint at such dark satellites. Stellar streams show disturbances that can't be explained by known satellites. Something is perturbing these streams, creating gaps and overdensities that suggest encounters with massive objects. Those objects might be dark satellites, invisible but gravitationally influential. If these dark satellites exist and are numerous, they could be a major source of mass loss. They'd be ejecting stars continuously without us being able to identify the cause directly. The Milky Way would be under constant bombardment from gravitational interactions with objects we can't see. The satellite threat extends beyond direct gravitational effects. Satellites falling into the Milky Way bring their own dark matter halos. These halos can sink toward the galactic center, depositing dark matter in the inner galaxy. This changes the dark matter distribution, altering the gravitational potential in ways that affect stellar orbits throughout the galaxy. Some research suggests that infalling satellites might have deposited so much dark matter in the Milky Way's centre that the central density is higher than expected from the original halo. This concentrated dark matter could affect stellar motions near the galactic centre, potentially even influencing the supermassive black hole's behaviour. The satellites are also competing for material. Gas falling into the Milky Way from the intergalactic medium might be intercepted by satellites before reaching the main disk. This starves the Milky Way of fresh fuel for star formation while feeding the satellites, allowing them to persist longer than they otherwise would. In this view, satellites are parasites, living off their host galaxy, weakening it over time. The Milky Way feeds them with gas that should have fed the central disk, empowering its own destroyers. This might sound dramatic, but it's supported by simulations and observations. The relationship between galaxies and their satellites is not benign. It's competitive, sometimes destructive, always consequential for both parties. The satellite assassins are reshaping the Milky Way from the outside in. They can't destroy the core. The central regions are too dense and too strongly bound, but they're eroding the edges, stripping away the outer disk and halo, removing stars and gas that would have remained part of the galaxy indefinitely. Over billions of years, this erosion will transform the Milky Way. The galaxy might end up smaller, more compact, with a denser core but depleted outer regions. Or it might be disrupted more dramatically if particularly massive satellites fall in at inopportune times. We're watching this process unfold in real time, or at least in astronomical real time. The satellites are killing the Milky Way slowly, over timescales vast by human standards but brief by cosmic standards. And there's nothing we can do but observe and try to understand. The mass loss plaguing the Milky Way has exposed a crack in our understanding of dark matter. If stars are escaping the galaxy, dark matter should be escaping too. But our models of dark matter distribution don't predict this. Something is wrong with either our observations or our theory. Dark matter dominates the Milky Way's mass. For every kilogram of visible matter, stars, gas, planets, there are roughly 5 kilograms of dark matter. This invisible substance creates the gravitational potential that holds the galaxy together. Without it, the Milky Way would fly apart. Stars orbit too fast to be held by visible matter alone. We detect dark matter through its gravitational effects. We can't see it, can't touch it, can't interact with it except through gravity. But we can measure how fast stars orbit and deduce how much mass must be present to keep them bound. The answer is always more than we can see, and that excess is dark matter. The standard model of dark matter assumes it's composed of weakly interacting massive particles, WIMPs. These hypothetical particles have mass but don't interact electromagnetically, making them invisible. They clump under their own gravity, forming halos around galaxies. In this model, the Milky Way's dark matter halo extends far beyond the visible disk, creating a roughly spherical distribution of invisible mass. Stars orbit within this dark matter sphere, held by its combined gravitational pull. But if stars are escaping, it implies the dark matter halo is weaker or differently shaped than models predict. Either there's less dark matter than we thought, or it's distributed differently, or it behaves differently than standard WIMPs. Each possibility is troubling. Less dark matter means we've been overestimating the Milky Way's mass. Our calculations of orbital velocities and escape velocities would be wrong. The galaxy would be lighter, its gravitational influence weaker, its structure less stable than assumed. Different distribution would be equally problematic. If dark matter is lumpy rather than smooth, or elongated rather than spherical, it changes how stars respond to gravitational perturbations. Lumpiness could explain why some stars escape unexpectedly. They pass through regions of lower dark matter density where gravitational binding is weak. Different behaviour is the most radical possibility. What if dark matter doesn't behave like standard WIMPs? What if it has self-interactions, allowing dark matter particles to collide and exchange momentum? Or what if dark matter decays, slowly disappearing over cosmic time? These alternatives are speculative but not ruled out. Dark matter remains mysterious. We've never detected dark matter particles directly, despite decades of experiments. We infer their existence from gravitational effects, but we don't know what they are or exactly how they behave. The Milky Way's mass loss might be a clue. If we can figure out why stars are escaping despite the dark matter halo, we might learn something fundamental about dark matter itself. One intriguing possibility: dark matter is escaping along with visible matter. As stars are ejected from the galaxy, they carry dark matter with them. The gravitational interaction that ejects a star also disturbs nearby dark matter, sending it on escape trajectories. If this is happening, the Milky Way is losing both visible and dark matter simultaneously. The total mass loss would be much larger than calculations based on stellar escape alone suggest. The galaxy might be shedding dark matter at rates that significantly reduce the halo mass over billions of years. Testing this hypothesis is difficult because we can't observe dark matter directly, but we can look for indirect evidence. If dark matter is escaping, the density profile of the halo should change over time. The outer regions should become less dense as material escapes, while the inner regions remain relatively unaffected. Observations of stellar velocities at different galactic radii could detect such changes. If outer stars orbit more slowly than expected based on static dark matter models, it would suggest the halo is lighter than it should be, possibly due to mass loss. Preliminary results are ambiguous. Some observations hint at lower than expected halo mass in the outer galaxy. Others find no discrepancy. The data quality isn't yet good enough to definitively say whether dark matter is escaping or not. Another approach involves studying other galaxies. If the Milky Way is losing dark matter, other galaxies should be too. Comparing dark matter content across galaxies of different ages and environments might reveal systematic mass loss patterns. Such studies are underway, but they face challenges. Measuring dark matter content in other galaxies is even harder than in the Milky Way. We have less detailed data about stellar motions in external galaxies, making it difficult to constrain their dark matter distributions precisely. Some researchers propose that dark matter loss could explain certain puzzling observations in galaxy evolution. For instance, satellite galaxies often appear to have less dark matter than simulations predict. This too big to fail problem might be solved if satellites lose dark matter as they orbit within their host galaxy's halo. The interaction between satellite and host could strip dark matter from the satellite, just as it strips visible matter. Over time, satellites would be depleted of dark matter, leaving them lighter than predicted by standard formation scenarios. If this is correct, the Milky Way satellites are both victims and perpetrators. They're losing dark matter to the Milky Way, while also helping strip dark matter from the Milky Way through gravitational interactions. It's a complex dance of mutual destruction. There's also the possibility that dark matter isn't dark at all, in the way we think. Modified theories of gravity, such as MOND, modified Newtonian dynamics, attempt to explain galactic rotation curves without invoking dark matter. Instead, they propose that gravity works differently on galactic scales than Newton and Einstein predicted. In these theories, there is no dark matter halo. The faster than expected orbital velocities are explained by gravity being stronger at large distances than inverse square law predicts. If MOND is correct, the Milky Way's mass loss doesn't involve dark matter because dark matter doesn't exist. Most physicists are skeptical of MOND. It struggles to explain observations on larger scales, particularly in galaxy clusters and the cosmic microwave background. Dark matter models work better overall, even if they have some puzzles. But the Milky Way's mass loss adds a new puzzle to the dark matter paradigm. If standard dark matter can't explain why stars are escaping, maybe we need to revisit alternatives or modify our understanding of how dark matter behaves. The dark matter crisis extends beyond just the Milky Way. Cosmologists use observations of galaxies to constrain dark matter properties. If those observations are systematically wrong because we've been ignoring mass loss, then cosmological conclusions might be wrong too. The amount of dark matter in the universe, its clustering properties, how it interacts with visible matter, all of these could need revision. The mass loss problem isn't just about one galaxy. It's potentially a fundamental challenge to our cosmological framework. This doesn't mean dark matter theory is wrong, but it might mean we've been implementing it incorrectly. The devil is in the details, and details like mass loss can dramatically affect outcomes even when the basic theory is sound. Resolving the dark matter crisis requires better observations and better models. We need more precise measurements of stellar velocities throughout the galaxy. We need improved simulations that correctly implement gravitational interactions between satellites and host galaxies. We need to test whether dark matter behaves exactly like standard WIMPs, or whether it has additional properties we've been ignoring. This is active research with no clear answers yet. The mass loss observations are too recent for complete theoretical understanding. Scientists are still debating what the observations mean and how to incorporate them into existing frameworks. But one thing is clear: the mass loss problem has revealed gaps in our understanding of dark matter. Whether those gaps indicate minor corrections or major revisions remains to be seen. The Milky Way's disintegration might ultimately teach us more about the invisible substance dominating the galaxy than about the visible stars we're losing. The Milky Way's current troubles are just the beginning. In about 4 billion years, our galaxy will collide with Andromeda, the nearest large spiral galaxy. This collision will be the ultimate test of whether the Milky Way can hold itself together, or whether the disintegration we're currently observing is an omen of total destruction. Andromeda is approaching at roughly 120 kilometers per second. That sounds fast, but at galactic distances, it translates to a slow-motion collision spanning billions of years. The galaxies will approach, pass through each other, separate, then fall back together in a gravitational dance that might take several billion years to resolve. During this dance, both galaxies will be torn apart and reassembled. Stars will be scattered. Gas clouds will collide and form new stars at unprecedented rates. The supermassive black holes at both galactic centers will eventually merge in one of the most energetic events possible in the universe. For the Milky Way, already losing mass and structurally weakened by satellite interactions, this collision could be catastrophic. A stable, healthy galaxy might survive a merger relatively intact, its stars settling into new orbits in the merged remnant. But a galaxy that's already coming apart might be completely disrupted, its stars scattered across intergalactic space. Simulations of the Milky Way-Andromeda merger typically assume both galaxies are currently stable. They model the collision as two pristine spirals encountering each other for the first time. But if the Milky Way enters the collision already weakened, already hemorrhaging mass, the outcome could be very different from standard predictions. A weakened Milky Way might be unable to hold together during the first pass through Andromeda. Tidal forces during the encounter could strip away the outer disk entirely, sending billions of stars into intergalactic space. What remains might be only the dense central core, too tightly bound to be disrupted even by a major collision. This would transform the Milky Way from a majestic spiral galaxy into a stripped core, a compact elliptical remnant containing only a fraction of its original stellar population. The merger would then be between Andromeda and this diminished remnant, producing a final galaxy dominated by Andromeda's original mass. Future inhabitants of that merged galaxy, if any civilization survived the chaos, would look back and realize the Milky Way contributed relatively little to the final system. Future inhabitants of that merged galaxy, if any civilization survived the chaos, would look back and realize the Milky Way contributed relatively little to the final system. Andromeda would dominate the mass, the structure, the gravitational hierarchy. Our galaxy, once a sprawling spiral with sweeping arms, would be remembered as a wounded participant, already bleeding stars before the first close encounter even began. This possibility has forced astronomers to rethink merger simulations from the ground up. Traditional models assume conservation. Mass redistributes, energy dissipates, structures reassemble. But those assumptions break down when one of the participants is already losing matter faster than expected. A galaxy that is actively shedding stars does not behave like a closed system. It behaves like something unstable, something failing to hold itself together under stress. And stress is exactly what the Andromeda encounter will deliver. As the two galaxies approach, their dark matter halos will interact long before their visible disks touch. These halos, vast and diffuse, will overlap first, creating enormous tidal forces that ripple inward. Stars in the outer Milky Way, already on the edge of escape, will feel those forces most strongly. For them, the collision won't be a future event. It will begin hundreds of millions of years before the galaxies visually overlap. Every close approach will act like a gravitational slingshot. Stars that survive satellite perturbations and dark matter irregularities may finally be pushed over the threshold. Escape velocity will be exceeded not by explosive violence but by subtle cumulative nudges, orbital resonances stacking until gravity loses its grip. The Milky Way's outer spiral arms may not survive the first pass at all. Instead of being stretched and distorted, as in classic merger illustrations, they could simply unravel. Stars would peel away in long arcs, forming enormous tidal tails that stretch hundreds of thousands of light years into intergalactic space. Some will fall into Andromeda, many will fall into nothing. Between the galaxies lies a growing graveyard of orphan stars, and unlike supernovae or black hole mergers, this destruction will be silent. No flashes, no explosions, just stars drifting away, one by one, into permanent isolation. Closer to the centre, the story is different. The Milky Way's core is dense, compact, and deeply bound. The bulge stars and the supermassive black hole Sagittarius. A star are unlikely to be ejected. They will survive, but survival does not mean stability. As Andromeda passes through, gravitational torques will scramble stellar orbits. The orderly rotation of the disk will be replaced by chaotic motion. Stars will be flung onto elongated, tilted, or even retrograde orbits. The very concept of a galactic plane may cease to exist. Gas clouds will collide at high speeds, compressing violently and igniting intense starbursts. For a brief cosmic moment, the merged system will blaze with newborn stars. But this will come at a cost. Starbursts consume gas rapidly. Combined with the Milky Way's ongoing gas loss, the fuel for future star formation could be exhausted far sooner than expected. The collision may accelerate the galaxy's transition from a living, star-forming system into a quiet, aging remnant. In other words, the merger might not rejuvenate the Milky Way. It might finish it. What makes this particularly unsettling is timing. The Milky Way is not waiting passively for Andromeda. The disintegration we're observing now means the galaxy is entering the collision already compromised. Every star lost today is one less anchor tomorrow. Every destabilized orbit makes future stripping easier. This is not a single disaster. It's a cascade, and the cascade has already begun. The most disturbing realization to emerge from all this is not that the Milky Way is losing stars. It's that the galaxy may no longer be in equilibrium at all. For decades, astronomers assumed the Milky Way was a mature, dynamically settled system. Not static, but balanced. Forces cancelled. Orbits averaged out. Disturbances faded with time. That assumption underpinned nearly every model of galactic behaviour. But equilibrium leaves fingerprints, and those fingerprints are missing. When researchers mapped stellar motions across the galaxy using Gaia's data, they expected symmetry. Instead, they found ripples, warps, waves moving through the disk like vibrations in a struck bell. The Milky Way is ringing. Stars above and below the galactic plane oscillate in patterns that shouldn't exist in a relaxed system. Entire regions move coherently, as if responding to a recent disturbance. But there was no recent major collision. No obvious trigger. Unless the trigger was internal, mass loss itself can destabilize a galaxy. As stars escape, the gravitational potential changes. Orbits that were once stable become marginal. Marginal orbits become unbound. This creates a feedback loop. Loss causes instability. Instability causes more loss. In physics, this is called runaway behavior, and runaway systems do not self-correct. The disk warp, long observed but poorly understood, may be a symptom of this imbalance. The Milky Way's disk is bent, twisted, like a vinyl record left too long in the sun. Astronomers once blamed satellite interactions alone. Now that explanation seems incomplete. A weakening gravitational backbone would make the disk more susceptible to warping from even small perturbations. The galaxy becomes flexible, fragile, easy to deform. Even the sun's motion carries a clue. Our star does not orbit smoothly. It oscillates up and down through the galactic plane, a motion long considered normal. But recent measurements suggest those oscillations may be changing. Subtly, gradually. That implies the restoring force pulling stars back toward the plane may be weakening, which means the Milky Way's gravitational structure is changing in real time. This loss of equilibrium also affects timescales we thought we understood. Stellar migration, the slow drifting of stars inward or outward over billions of years, may accelerate in an unbalanced galaxy. Regions that were once stable nurseries may empty. Others may become overcrowded. The concept of galactic neighborhoods breaks down. An equilibrium loss doesn't stop with stars. Dark matter responds too. If the visible mass distribution changes, dark matter rearranges itself. That rearrangement feeds back into the visible system, further altering orbits. It's a coupled instability, like removing beams from a bridge while traffic is still flowing. The most unsettling implication is this: the Milky Way may not naturally settle back into equilibrium before the Andromeda collision. The timescale for relaxation could be longer than the time remaining before impact. If so, the galaxy will enter the merger in a dynamically excited state, vibrating, warped, already shedding material. That dramatically increases the chance of catastrophic stripping, which raises a chilling possibility. The Milky Way we know may never exist again in any recognizable form. On human timescales, all of this feels abstract. The stars are not visibly fleeing the sky. The Milky Way still arches overhead on dark nights. Nothing feels wrong. But cosmic processes do not care about perception. The sun is roughly halfway through its life. In another 5 billion years, it will swell into a red giant and die. That timeline overlaps uncomfortably well with the Andromeda collision and the Milky Way's continuing mass loss. Our solar system is unlikely to be ejected entirely, but it will not be untouched. Stellar encounters will become more common as orbits scramble. The night sky will change dramatically. Andromeda will grow from a faint smudge to a dominating presence, stretching across the heavens. If humanity, or any successor civilization, still exists, the sky will tell a story of decay and collision. More subtly, the galaxy's changing mass affects cosmic radiation environments, gravitational tides, and long-term orbital stability. These are not immediate threats, but they are not irrelevant either. The Milky Way is the gravitational ecosystem that shaped Earth's history. Its structure influenced comet influx rates, supernova distributions, radiation backgrounds, changed the galaxy, and you change the long-term context of life. And then there's the psychological weight of it. For most of human history, the galaxy was permanence itself. Empires rose and fell beneath an unchanging sky. Even modern astronomy treated the Milky Way as a stable stage on which cosmic drama unfolded elsewhere. Now we know the stage itself is cracking. Our galaxy is not a sanctuary. It is not eternal. It is not even particularly stable. We live inside a structure that is slowly losing coherence, shedding pieces into the void, drifting toward a collision that will erase its current identity entirely. This doesn't make existence meaningless, but it does make it fragile. And perhaps that fragility is the point. The Milky Way is not exploding. It is not collapsing. It is doing something far more unsettling. It is unraveling. Quietly, gradually, relentlessly. Stars leave without ceremony. Gas drifts away without sound. Structures weaken not in moments of drama, but through accumulated imbalance. The galaxy is aging, not gracefully but unevenly, like a living system losing its ability to heal. What astronomers are witnessing is not an anomaly. It is a phase we failed to anticipate because we assumed permanence where there was only temporary order. The Milky Way will not vanish. Something will remain. A core, a remnant, a merged descendant dominated by Andromeda. But the spiral galaxy that defined our cosmic identity is already changing into something else. And that process has already crossed the threshold of observability. We are watching our galaxy fall apart. Not as a sudden apocalypse, but as a long goodbye written in stellar streams and gravitational whispers. A farewell measured in millions of years, yet happening fast enough that our instruments can catch it in the act. For the first time, humanity knows that even our largest home is temporary. And once you know that, you can never look at the night sky the same way again. Because the Milky Way above you is not just beautiful, it is wounded, and it is moving toward an ending we are only beginning to understand.